Hello everyone, my name is Edison Hong and this is my first lab, Constant Velocity for Physics. So, what are we going to be doing today? We're going to be going through the purpose of this lab, Newton's first and second law, how they apply to this lab, the experiment through computational models, comparison of the observed and predicted, and our conclusion on what the results mean and further questions. Now, what is the purpose of this lab? So, what's the purpose of this lab? It's to observe Newton's first and second laws through motion of an object at constant speed without changing any direction. And we're going to analyze this through my water bottle rolling on a desk in a software called Tracker and capturing the time intervals and comparing it with the GlowScript computational model. So, what are Newton's first and second laws? Newton's first law is an object at rest remains at rest, or if it's in motion, remains in motion, unless acted by a net force. And Newton's second law, the momentum principle, is net external force equals the change in momentum of a system divided by the time over which it changes. So, what can we derive from Newton's second law? So, as you can see here, Newton's second law is F net equals momentum over time. And we can derive the momentum update formula from this. And then from that, we can derive the velocity update formula. We'll also be using the position update formula. And in this case, since there's no change in velocity, it means the net force is zero. So all forces cancel out, and it's in equilibrium and results in a constant velocity motion. So, experiment time. So, I'm going to assume that there's no friction, no air resistance. The normal force is the gravitational force on the flat surface, and we're only observing displacement in the x-axis and nothing on the y-axis and z-axis. So, we're going to be observing my bottle going on a flat black surface in a constant velocity motion, and on the side here, it's going to be recorded on a graph going on an upward slope, and the values determined by my keyframes. So from the previous tracker video that you saw there, I got the time from the graph in the first column. The second is the x position from the graph, and the third is the initial velocity that I calculated here. So the total time it took from the start to the finish of the bottle rolling was 1.87 seconds. Initial position was negative 546 meters, and the initial velocity was the second position minus the first position over the two times there, which resulted in 723 meters per second. So, looking at our computational model here, I set the net force to 0, and I inputted our initial velocity and initial position, set delta t to 1 over 30 since it's recorded at 30 frames per second. The mass of the ball doesn't really affect velocity here, so I set it to 0.01, and the position formula predicts the location here. So the computational model graphs here show the position being on a positive slope over time, and the velocity here is being constant as we assumed before. So, comparing observed versus predicted. So, our predicted line seems to be slightly above it in position over time, and our observed is a little bit below our predicted over time. So some of our possible errors would be position tracking, which could diverge from the precise results, outside forces, which could be like friction and air resistance, or rounding in numbers. So what do our results mean, and what if our data was flipped? So what do these mean, and how many pushes and pulls could be determined? So it's actually not possible to determine how many pushes and pulls there are for a zero net force. I'm pushing the bottle at a constant velocity, but it's not possible to prevent my bottle from accelerating due to forces like friction or air resistance between my bottle and the surface. Also, some forces are too small to measure. So, what if our x-axes were flipped? The only difference is that the slope of the graph would be in the negative direction now. The velocity would still maintain the same magnitude though. And this is it. And thank you so much.